Welcome to analyzing quadratic functions for pre-calculus of Math 11. We're taking a look today at factored form of quadratics, which is section 4.6. We've seen in the past that what we can do is we can complete the square to graph a quadratic function. In this unit, we're going to take a look at another technique for sketching quadratic functions, which is something I call the factor/intercept method. And sketching a curve this way makes use of clearly the intercepts of the functions. So what we do is we take a look at both the x-intercepts, typically called zeros, and the y-intercept. So if we let x equal 0 in an equation, so think of any equation, when you let x equal 0, which is basically you're sitting on the y-axis, we see that the constant term in the equation is the y-intercept. On the other hand, if we let y equal 0, which is us trying to find, if we let y equal 0 and factor the function, we can determine the x-intercepts. And x-intercepts, we also use the word zeros. So let's determine very quickly here the x and y-intercepts of the function y equals x squared minus 2x minus 15. Let's talk about the y-intercepts first. So we have the y-intercepts. You find the y-intercept of a function by letting x equal 0. So let's plug in 0 for all the x's. And pretty quickly we get to see that 0 squared minus 0, so that's still 0, and we're left with a y value of negative 15. So the y-intercepts of that function is negative 15. X-intercepts are zeros. We're going to find by letting y equal 0. Now, what happens is we end up with a quadratic expression that we need to factor, solve this equation. Very quickly, that factors into x minus 5, x plus 3. And solving, we get that x equals negative 3 and 5. So, we find that the y-intercept is negative 15. We find that the x-intercept is negative 3 and 5. Further to this, because the vertex sits on the axis of symmetry, so we've seen in previous sections that the axis of symmetry, the imaginary line that balances our graph, cuts our graph in half, sits directly on the vertex. What we can do is we can use the average of the x-intercepts to determine the x-coordinate. Of the vertex. So let me do a quick sketch here. Let's say we have two zeros forming a parabola, and the axis of symmetry cuts straight down the middle of that graph through the vertex. Because the two zeros are balanced both to the left and to the right, basically right in between the two has to be the vertex. That's really why this works. And because the coordinates of the vertex is an ordered pair, we can plug the x-coordinate into the original function to find the y-coordinate of the vertex. So we have a nice little technique here. What we're going to do is we're going to find the coordinates of the vertex of the graph of the function y equals 2x squared plus 7x minus 4. So let's find the y stuff first. We know that if we, let's find the x-coordinate first. Let y equal 0. We get 0 equals 2x squared plus 7x minus 4. We can factor that. Again, I'm not going to go through those techniques. That's in past units. That factors into 2x minus 1 and x plus 4. We end up with either 2x minus 1 equaling 0, which is 2x equals 1, which is x equals a half. So there's one of the zeros. And we have x plus 4 equals 0, which leaves us with another x-intercept or a 0 of negative 4. So we could sketch that way. That helps. But we could certainly find the x value of the vertex, and we just write it as x vert, by finding the average of those two values. So the average of those two values would be add the two together and divide by 2. That's just a standard average. I'm going to find a common denominator here because we are talking about fractions. That'd be 8 halves all over 2. X vert 1/2 minus 8 halves is negative 7 halves, all divided by 2. When you divide by a fraction like that, what happens is we get that the x vertex, the coordinate of the vertex, is negative 7/4. So great, we now have the x coordinate of the vertex. Because that vertex appears on the curve, we can plug in that x value into the curve function, into the equation of the function, and find the y value. So the y vert has to equal us plugging 7/4 in to the function. Sorry, negative 7/4 into the function, and solving. Now certainly you could do this using your calculator, getting a nice decimal answer. I'm going to do it exactly just to show that it's not terribly difficult. Squaring negative 7/4 would be 49/16. 7 times negative 7 is negative 49/4 minus 4. We multiply by 2, which really just reduces, so that's 49/8. Looks like everything needs to be converted to eighths, so let's find a common denominator by multiplying negative 49/4 by 2's. That will give us negative 98/8. And turning 4 into something over 8 would be multiplying by 8, so that would be 32. And we see that we get a value of negative 81/8. So the vertex of this parabola is located at negative 7/4, negative 81/8. Not a very great point to sketch if we had to do that, but certainly the technique is going to remain the same no matter what. So let's take a look at another example here. Basically the same thing. What I want you guys to do is sketch the graph using the factor-intercept method. So what you're going to do is you're going to draw points based on the intercepts and the vertex. So why don't you hit pause here if you think you know what you can do. Go ahead, try and solve that. And if not, I'll help you out in a second. So if we start with the y-intercept is just the constant, which is 6. The x-intercepts are going to come from letting it equal 0, so negative 2x squared minus 4x plus 6. One of the easiest ways to do this is to factor out a negative 2, leaving us with x squared plus 2x plus 3. And that factors into x plus 3. Apologies. Sorry, that should be a negative 3 on the end there. Factors into x plus 3 and x minus 1. And what we end up with is x-intercepts of 1 and negative 3. So the x-vertex is going to be the average of those two. So 1 plus negative 3 over 2. Fairly simple calculation. 1 plus negative 3 is negative 2 over 2. And we get an x-vertex of negative 1. The y-coordinate of the vertex is us plugging negative 1 into the function. Negative 2 times negative 1 squared minus 4 times negative 1 plus 6. Negative 2 times 1 plus 4 plus 6. Negative 2 plus 10. And we get a value of 8. So negative 1 comma 8 is our vertex. So we have lots of bits of information here that we can use. We have the x-intercept, we have the y-intercept, the x-intercept, and the vertex. And that's enough to give us a reasonably good sketch. Let's take a look here. Y-intercept of 6. Let's draw a dot at 6. Let's try and draw it at 6. There we go. The vertex at negative 1, 8. So negative 1, 8 puts it right there. We have x-intercepts of 1 and negative 3. You see how we can draw in, let me just sketch in very lightly here, the axis of symmetry Notice how the x-intercepts are nicely balanced between that, 2 units away. That actually lets me know that there's another point we could draw on this curve, which is the reflection kind of that y-intercept. And this is a reasonably good sketch. We have enough points here to really draw a nice curve. Not exact, I wouldn't call it graphing because we're not doing a solid kind of basis for this where we find points or we graph it like we typically do, but a pretty good sketch. So finally, the graph of a quadratic function has zeros -3 and 5, and it passes through the point 6, -27. Determine the general form of the equation. This is basically just the reverse process. We have that the zeros of the function are -3 and 5. So what that means is that x equals -3, x equals 5. Trying to solve it for 0, adding 3 to both sides, we get x plus 3 equals 0, x minus 5 equals 0. And therefore, x plus 3 and x minus 5 are factors. So what you do is you actually back solve. You start them equaling the 0 and move backwards to make them equal 0. So our equation is x plus 3, x minus 5, but there might be a little bit of a stretching effect. So let's plug an a in there. We don't really know what that a value is yet. But we can figure it out by, if we plug in the point that we're given, which is 6, -27. So y is -27. A, we don't know so much. 6 plus 3, 6 minus 5. 6 plus 3 is 9. 6 minus 5 is 1. And let's take a look here. We got -27 equals basically 9a. Dividing by 9, we get a equals -3. So we get y equals -3, x plus 3, x minus 5. So that would be in kind of a factored form. It asked for general form, so let's expand that. Let's leave the -3 alone for a second. We get x squared minus 2x minus 15. And multiplying through by -3, we get -3x squared plus 6x plus 45. So there it is in general form, which we could go then and take it into some sort of standard form, factoring it, completing the square, that sort of thing. This ends the notes for Pre-Calculus Math 11, analyzing quadratic functions, the factored form of quadratics.